All right, let's go through how to integrate. And more specifically, let's go through how to take a ground reaction force and turn that into acceleration of the center mass, turn that into velocity of the center mass, and turn that into the position of the center mass. All right, so we got to do a couple things here. We're gonna do a counter movement jump, and we're gonna look at a ground reaction force profile during the counter movement jump, and then use that to generate position, velocity, and acceleration of the center mass. So let's start with the kinetic analysis. And remember, when you do a kinetic analysis, you identify the forces. Analysis, talking and writing at the same time. Kinetic analysis, we identify the forces acting on the object. In this case, we're going to do counter movement jump. And let's just draw a quick stick figure of someone standing on a force platform. This being the ground. And they're going to do a counter movement jump. This the side profile, so we're only seeing one leg here. So what forces are acting on the person? Well, we know gravity is pulling down on the person, and the other force is the ground reaction force. Now remember, the ground reaction force is a three-dimensional force. But right now, I just want to deal with looking at the person going up and down. So we're going to look at only the vertical direction. We're not going to concern ourselves with the medial lateral or the anterior posterior component of the ground reaction force. So once we identify all the forces acting on the person, we put them in Newton's second law, and that gives us a product of mass times the acceleration of the center mass. So what forces do we have here? We've got ground reaction force, which we're only going to deal with the vertical direction. That's an upward directed force. Up is positive, so that's going to be a positive force. Minus, or let me do plus Fg equals MACOM. Now that's a negative force because it's pulling down on the person. And so now we have two forces acting on the person. They add up to the product of mass times the acceleration of the center mass, and that's the center mass. That's the point of application. This is, in essence, the center mass here, and that's where we look at gravity acting on. All right, so now if we want to find the acceleration of the center mass, all we do is rearrange this equation. ACOM equals FGRF minus FG divided by M. And then we'll get the acceleration at the center mass due to the ground reaction force. Now, the mistake a lot of people make is they say these two forces are in opposite directions. And sometimes people will say, oh, and they're equal in magnitude. And that's Newton's third law. And that is incorrect, because these two forces are not always equal and opposite to each other. Well, they tend to always be opposite to each other for the most part, but not always. And the magnitudes are not always the same. In fact, if the ground reaction force is greater than the force due to gravity, body weight, that acceleration is going to be positive. Just because the numerator would be positive, that has to be positive. If the ground reaction force is less than the force due to gravity, less than body weight, acceleration will be negative. Now remember, direction of acceleration does not indicate direction of motion. So just because I said acceleration is positive or negative, that doesn't tell us which way the person is moving, and whether or not velocity is speeding up or slowing down. But we're going to need this. We're going to need this equation right here in order to determine the acceleration of the center mass due to the ground reaction force, because in our lab, we'll measure the ground reaction force. We'll look at it, and then we'll use that information to ultimately derive kinematic information. We do that through this equation. Okay, so let's do a quick little review of PVA, position, velocity, acceleration. And whenever I draw these plots, I always stack them on top of each other. This is position. This is velocity. Positive, 0, negative. And this can be any dimension, but we're going to be thinking vertical. And then acceleration. Positive, 0, negative. And always time on the x-axis. Okay, so if I have some position data, I can determine the velocity data by looking at the slope of this line and actually calculating the slope of this line. What's slope? Slope is rise over run. Rise over run, or change in the y-axis over the change in the x-axis. Writing time there. Change in y is change in position over change in x, change in time. That's velocity. So everything we know about velocity can be determined from the position versus time plot. And what we do is we take the derivative, that's what this means, to determine derivative. Oh my gosh, this is terrible spelling. Derivative. It's been a long day. Derivative. Close enough. We take the derivative. What we're doing is calculus. And what we do is this delta t, we try to make that as small as possible. Now, right now, it looks big because of the way I drew this, but this could be, that interval could be 1/1000th of a second. Could be 1/2000th of a second. Okay, that's our sample rate of our instruments. Could be 1/100th of a second, whatever it is. But we're going to take the derivative, we're going to take the slope between these two data points, and that's going to tell us what our velocity is. I'm going to put that dot right there, which is sort of the middle point of this time interval here. And that's our velocity. Okay. Now, let's say that position does something else later on, just so I can have, let's say it does something like this. Well, that's a negative slope. I'm going to put a negative line here, and I'm going to connect those dots right here, which is in essence what we do. Now, we try to line up these data points. There's some tricky math that we use when we start processing the data, but this is a negative slope. Velocity has to be negative. So now I've got this line that I'm connecting here. Well, again, if we look at the slope of this line, rise over run, change in y over change in x. In this case, it's change in v over change in t. You know that to be acceleration. That's the equation for acceleration. So everything we know about acceleration can be determined by taking the slope of the velocity versus time plot, or where you take the derivative once again, and we get the next parameter, which is acceleration. So derivative of position versus time gives us velocity. Derivative of the velocity gives us acceleration. Okay, so that's just a review. I think most of you are comfortable doing that. Now what we're going to do is integrate. Integrate means we're going to go in the other direction. We're going to start at the acceleration. We're going to determine velocity. Then we're going to take velocity and then determine position data. So this is integrate. I think I can spell that a little better. Integrate. So taking the derivative, going this direction, doing the integral, going in this direction. What's the integral? The integral is simply the area under the curve. Okay, so let's look at that. Okay, so I'm going to just do a velocity, or let me do actually something a little more basic. I'm just going to do x and y, a spatial plot. And I'll draw a box. And I'll ask you, how do you calculate the area of that box? Well, you know the area of a box is equal to length times width, or height times width, whichever way we want to do it here. In this case, that's delta, that's y, okay, whatever that is, times x, or times this interval right here. So I actually better put the delta x in there, and I better put the delta y in here, just so we can see it a little better. And that's going to give us our area. Okay. Now let's say now that's pretty simple. Well, don't lose sight that this is actually really quite simple. Well, let's say we have another plot or another situation that looks like this. And I say, calculate the area under that line, under that curve. What would you do? Well, hopefully you can see it. You keep this simple. I'm going to drop these dotted lines down here. And now I have 3 rectangles. R1, R2, and R3. And you should easily see that the area under this entire curve is simply the sum of those 3 areas. So area equals R1 plus R2 plus R3. I have a hard time writing today. Plus R3. So how do we calculate R1? Well, we calculate this delta y here. We calculate this delta x here. How do we calculate R2? We calculate that area, or excuse me, that delta y there, and this delta x, and then R3, we calculate that delta y and that delta x. It's that simple. And by integrating under this curve, we're actually determining the next parameter up, which we're going to see here in a second. Okay, so let me get rid of this. And now, let me do that. Let me draw. I'll do it this way. I'll do acceleration, meters per second squared, time, and right above that, I'll put velocity. Meters per second and time. Okay, let's say my acceleration plot looks something like, we'll just keep it simple, like that. Okay. For those of you who have worked in the lab, this is what the data would look like if you really zoom in on the data. Because these time intervals here would be 1/1000th of a second apart, typically when we're dealing with accelerometers. Okay. Well, let's look at the area under this curve here. Okay. Now what I'm going to do is I'm actually going to call this data point 1, data point 2, data point 3. Okay. I know it seems odd I'm not putting a dot right there, but we're collecting data in time. And actually I could put one at 0 too, but I'm going to skip that right now, but I'm going to just keep it somewhat simple. So I've got this data point, and this data point. So times 0, 1/1000th of a second later, and then 2/1000ths of a second. You know what, sorry. I shouldn't have put it here. I should put it down here. Okay. All right, now I'm going to calculate the area under this entire curve and then see what happens to the data up here. All right, let's see. So we're going to do area 1 and we're going to do area 2. So area 1 we calculate as base times height. So the height is change in A times delta T. And what I'm going to actually do is only look at this data point here, and I'm going to use that to tell me how high this rectangle is here. Okay? So I'm going to just rewrite that as A times delta t. And I'm doing that purposefully so you look at that and say, oh, that looks like an equation. What equation is that? Well, let's look at this as A equals delta V over delta t. If I move that delta t over, I get delta V. This is that equation right there. But I have delta V here. What's delta V? It's final minus initial. All right, now I've got a little bit of a problem here. I know A because I have my data here. I know delta t because I know my time interval here. Vf will be the final velocity at this moment in time. And I don't know that yet. I also don't know Vi, which would be the initial velocity at time 0. Okay, I don't know these two parameters. I have two unknowns. And you know, if you have two unknowns in one equation, you can't solve that equation. So what's important is I need to know a velocity data point up here in order to properly integrate. And what I'm going to do is start with the concept, going back to the counter moving jump, where the initial velocity of the center mass is going to be 0. The person cannot be moving. As long as they're not moving, then their velocity is 0. Now, if I look at this equation again, now I know Vi, I've measured A, and I know delta t as my sample rate. And I have one unknown, Vf. So now I'm just going to rewrite this as Vf equals A delta t plus Vi. Now I can calculate my final velocity based upon the magnitude of acceleration for that time interval times the time interval plus the initial velocity at the beginning of the time interval. Now, this is going to be a positive product between acceleration and delta t. And I'm going to add to it 0. So I'm going to end up with a data point that's a positive velocity. What I've just done is I've integrated the acceleration plot and I've yielded velocity data for that time interval. Now look at this, that's a positive slope, which is exactly the magnitude of acceleration down here. All right, this is taking the derivative, this is taking the integral. We're integrating this area. Now I want to integrate this area. All right, so now that was A1. A2 is the same equation. Oops, same equation. The magnitude of acceleration times the delta t, so magnitude of acceleration right here, times the delta t, the sample rate. Okay, that's the area of that. Now, let's look at this. A delta t. But in order for me to use this equation here, now I need my initial velocity for that time interval. So now my initial velocity is not the initial velocity at time 0, it's the initial velocity at the beginning of this time period. Okay. So this initial velocity is actually the final velocity from the previous time interval. These will be the same values. And what I'm going to do is then I'm going to add to this velocity the product of magnitude of the acceleration and the delta t. Now this is a bigger area, so that means this is going to be a bigger slope. So I'm going to actually draw this up here, and I'm going to do something like that. If I take the slope of this line, I get the magnitude of acceleration. If I calculate the area in this, I get this section of the curve, and all I'm going to do is add that section of the curve to my previous section. And now I'm integrating the velocity versus time plot. And I'm going to have a line that will reflect the magnitudes of the acceleration at each time interval. Okay, all right, so this is part one, and this is the equation that we need. And when we do the integration from velocity versus time to position versus time, we do the exact same thing. We do V equals delta S over delta T, or we rewrite this as SF minus SI over delta T, S being position. And I rewrite that to solve for SF equals V delta T plus SI. That's the same equation as we already dealt with. Sorry about the mess up there. And this final is the final position for that time period, the 1/1000th of a second. The initial is the initial position at the beginning of that time period. All right. Okay, so I think we'll call this part one. And what I'll do next is go through how to do this in Excel. And believe me, I know I'm glossing over a little bit of details here. And some of the details you'll discover as you start doing these integration. And one detail is you might say, oh, a rectangle doesn't really connect those two dots very well. Maybe you want to use some other shape. Now, if I just look at this thin line I just drew, this is a triangle here, this is a trapezoid. Well, there's just another equation for a trapezoid. And we can calculate the area of that trapezoid knowing this length and knowing this length. It's just another way to do it. All right. So you can use a rectangle, or you can use another shape like a trapezoid, and then and see if you're going to end up being more accurate. It depends on the type of movement that you're looking at when you're starting to integrate the curve, and it depends on how big this delta t is right here. The smaller that delta t, the easier it is to justify using a rectangle, because that delta is really small. You're actually not going to be overestimating too much. The other part that we look at is if the curve is symmetrical, meaning that it increases as much as it goes back down, and that way we overestimate the area on one side of the movement and then underestimate it on another side, and we would, that error would balance out. The other part that I'm glossing over is where we are putting these data points relative to these curves. But if you get the concept down, you're going to be okay, because what I'm doing here is I'm lining up the new velocities. This would be initial velocity at the beginning of this time interval. This would be the final velocity in this time interval. This would then be the initial velocity for the next time interval and the final velocity of that time interval. Okay, I think that's it for part one of integrating. All right, watch for part two. Thanks.